distribution for transform section. Using that, please note that transform section, this stress distribution for transform section is going to be in terms of material 1. So what is the equivalent stress in material 2? That you can see the second sentence. Once you do that equivalent section analysis, get the stress distribution, and you can actually back calculate the stresses in material 2. The stress in F2, stress F2y. F2y is nothing but y is distance of a particular point from the neutral axis. Okay, stress F2y in material 2 can be expressed in terms of corresponding stress. This is equivalent stress, okay? Or transform section, whatever you did, transform section, you analyze it, and whatever stress you get, that stress value, F1y, this F1y you need to multiply with modular ratio, you are going to get F2y. Is this clear? So this transformation or this transform section, we are solely doing or mainly doing for the purpose of convenience and getting this stress distribution. And once we get this stress distribution for the transform section, we go back to the original section and try to find what are the stresses. Okay, if this concept is very clear to you, then we can proceed further. And last class I showed you modular ratio. Now whatever composite section we are going to deal with is reinforced concrete. In reinforced concrete, you have some reinforcement as well as concrete. So it's going to be a composite section made of 2 materials. So for that kind of thing, how to get the modular ratio? M, how do I get it? It's simply modular ratio. If you want to convert, you have steel as well as concrete. Once again, let's say our steel is F2. F2 is, or material 2 is steel, material 1 is concrete. Okay, with that understanding, modular ratio is defined as modulus of elasticity of steel to modulus of elasticity of concrete. Modular ratio M is ratio of modulus of elasticity of steel to modulus of elasticity of concrete. Modulus of elasticity of steel, irrespective of the different grades of steels, we suggested you, or if no specific value is given, you can take it as 200 GPa. So modulus of elasticity of steel is 200 GPa. What about modulus of elasticity of concrete? Short-term modulus of elasticity of concrete is given by 5000 root FCK. That is only for short-term. Okay, long-term effects are not actually taken care in that equation. EC is equal to 5000 root FCK, and long-term effects like creep and other things, modulus of elasticity is going to get affected. So what code is saying, IS 456-2000, what it is saying is modular ratio for different grades of concrete. It is giving an equation. It's giving an equation in IS 456 annexure B. Last class I already showed you that one. Okay, this is the equation under working stress method, annexure B, page 80. Modular ratio has the value 280 divided by 3 sigma CBC. Sigma CBC is nothing but C. This first C is for concrete. Okay, B is for bending and C is for compression. So stress in concrete, permissible stress in concrete under bending compression. Okay, so you can have compression due to bending. In table 21 in page 81 of IS 456, sigma CBC value for various grades of concretes it is given. And permissible stress in compression, you can read this title here, permissible stress in compression. This compression can happen due to bending. Because when you take some structural element and try to apply or subject it to bending, some fibers are going to be in compression, some fibers are going to be in tension, depending on whether you are applying sagging moment or hogging moment. So the fibers which are in compression region, okay, if the beam is made of concrete and those fibers are going to be made of concrete, and those there we need to see what is the maximum stress or permissible stress in compression under bending. Or you can take a concrete like in the form of like a column or something like that. You can subject it to direct compression. Under that case, this is the column. Okay, this number 3 of this table, that is giving you permissible stress in compression, which is direct compression, and this is bending. Our modular ratio is related to this one, sigma CBC, and here it is denoted as sigma CC. And in this column, we'll come back to this table at a later stage. We'll see where this is required. This is permissible stress in bond. Okay. So now you got the sigma CBC value from the table, and make use of this equation or modular ratio. M is equal to 280 divided by 3 times sigma CBC. This M here, this modular ratio M is ratio of modulus of elasticity of concrete to ratio of modulus of elasticity of steel to concrete. M is equal to ES over EC. Okay, that you make a note. You have a notebook with you whenever this class is there. Notebook and pen with you. M here, whatever is given in annexure B, M is ratio of modulus of elasticity of steel to concrete, not the ratio of modulus of elasticity of concrete to steel. Okay, not EC over ES. It is ES over EC. That you have to keep in mind. Okay. So you making use of this, for sigma CBC, you just go and see table 21. For different grades of concrete, you can actually tabulate in this manner. So that is what is given here. For using it readily, you can actually, or after working few example problems, after working with example problems, you may actually, you may not require to see this. Maybe you will automatically remember these values. Okay, different grades of concrete. What is the modular ratio? Any questions here? So now we are getting into reinforced concrete. Okay, so we just understood what is the concept of this transform section. Now take this example here, which is shown in the figure. A column. This is a section of a column. Okay, and the column is having dimension. This is a square column, T by T, or T is this dimension, T is this dimension. Okay, and this column is having 2 materials, reinforced concrete. Sorry, this reinforcement as well as concrete. Okay, reinforcement is shown here in the picture as some dots, filled circles. Filled circles, these 4 filled circles at 4 corners, they are the steel bars. Because we are looking in the section, we are looking at a section of reinforced column. This is how that longitudinal steel is going to be actually appear. And this steel, this is a column. Okay, this steel is going to be in compression. That's why ASC is used. Symbol ASC is used to denote the corresponding steel in compression. Okay, A is for area of cross section, S is for steel, C to show that indicate that the steel is in compression. You make a note of it in your notebook. You just draw this section and also make a note of this section. Okay, and this column is subjected to a load P. Okay, column is subjected to load P, and because of this application, because this is a compression load, because of this application of load, a strain is epsilon. Strain is epsilon. Okay, or if you take this column length to be unit length, automatically this change in length is going to indicate strain. Epsilon. Epsilon is the strain. So now this total load P is shared by this concrete as well as the steel. That is, let's read this, okay? So T by T is the total area of the column. So gross area, if AG is the gross area of column is denoted with AG. ASC is the total steel area in compression. Okay, are you noting down? AG is the gross area. Gross area is T by T here. And if you know the diameter of the steel bars, you can easily find what is the total area of steel. Okay, ASC. And what is the net area of concrete? Net area means actual area of concrete is total area AG minus ASC. That is what this one. Okay, you make a note of it. And what is the load that is applied? Total load P is applied, or when total load P when applied is resisted by combined action of concrete and steel. So I can write an equation like this: P is equal to area of concrete, net area of concrete, multiplied by the stress developed in the concrete, plus area of steel in compression, multiplied by stress developed in steel. Any questions here? P is equal to AC times sigma CC prime. Sigma CC prime is nothing but stress that is developed in concrete. When you subject this to a load P, okay, and the stress that is developed in the steel is sigma SC prime. Any question here? I can. This is a simple mechanics, okay. Whatever the load that is resisted by the concrete plus load resisted by the steel should be equal to the total load applied. Any questions here? And now an important concept here, when I subject this column to load P, I told this entire column, the strain in this column is epsilon. That means strain in concrete is also epsilon, strain in steel is also epsilon. Okay? And so epsilon is equal to, if stress in concrete is sigma CC prime, what is this epsilon? Epsilon is equal to sigma CC prime divided by modulus of elasticity of concrete. That is going to be your epsilon. Same way, this epsilon can also be found if you know the stress in steel, because of the load application. If you know the stress in steel, sigma SC prime, divide it with Young's modulus of steel, you are going to get strain. Okay, so strain epsilon is either it can be calculated from stress in steel or stress in concrete using the corresponding modulus of elasticity of steel or concrete, depending on what you are using. So this, you see this one, epsilon is equal to sigma prime SC divided by ES is equal to sigma prime CC divided by EC. I want you to note down this equation and look at its second and third parts of the equation. You rearrange this equation. You rearrange these second and third parts of this equation. Sigma SC prime divided by sigma CC prime is equal to ES divided by EC. I can rearrange this equation in that manner, okay? Or I can say sigma SC prime, I can take this ES to this side, then it becomes ES divided by EC sigma CC prime. So that is what this is. And just now we noted that ratio of modulus of elasticity of steel to modulus of elasticity of concrete, it is modular ratio M. Okay, so stress in steel in compression is equal to modular ratio of stress in steel in stress in concrete in compression. Okay, stress in steel in compression is equal to modular ratio times stress in concrete in compression. And what did we start with? I told you, let's start reinforced concrete. In that, let's assume material 2 is steel, material 1 is concrete. Okay, and at the beginning of this lecture, we noted this equation: F2 is equal to M times F1. F2 is nothing but steel. Stress in steel is equal to modular ratio times stress in concrete. Okay. So I'm going to substitute. You have this equation. I'm going to substitute this information in this equation. P is equal to AC times sigma CC prime plus ASC times sigma SC prime. In that SC, sigma SC prime, I'm going to replace that with this one. M times sigma prime CC. So then you are going to get this equation. And then you can rewrite this in this manner. Okay? Because sigma CC prime is here, sigma CC prime is here. This is this equation. So P is equal to, load applied is equal to sigma CC prime multiplied by what is AC plus M times ASC. What is that? Equivalent area, equivalent or transformed or equivalent transformed area in terms of concrete alone. Okay, area of steel. How did you take care of area of steel? Area of steel is replaced with equivalent area of concrete. Equivalent area of concrete is equal to modular ratio times area of steel in compression. Any questions here? So you agree with?
Okay, I think let me just add some concepts. See, this is a very important problem which highlights the basics of analysis of reinforced concrete members. See, there are essentially 3 principles to analyze this composite material. The first principle is equilibrium of forces. This equation that P is equal to the force carried by the concrete plus the force carried by the steel, this is the equilibrium equation, and we have to satisfy the equilibrium equation in any situation. The second principle is the compatibility of strains. See, these 2 materials, steel and concrete, they are deforming together, and we are bringing that, this is called compatibility of deformation in terms of strain. What we are writing is that the strain in the concrete is same as the strain in the steel, or let me put it the other way, the strain in the steel is same as the strain in the concrete around its vicinity. This is called the principle of compatibility. The third principle is called the constitutive models, so the constitutive relationships, which relate the stress in each material with the strain. Now, in this particular case, they're all considered to be linear elastic, this working stress method, and then we are defining the modular ratio and all. But in essence, we are having 3 principles here. First, equilibrium of forces. Second, compatibility of strains. And third, the constitutive materials. That's the constitutive models for the materials. Okay.
Any questions? And here, I want to slightly modify this equation. Basically, how did we introduce this steel? Steel is occupying by replacing some amount of concrete. Some amount of concrete is replaced by the steel. And what is the amount of that concrete? It is going to be same as area of this compression steel. Okay. So this equation, if you want to take care of that, this equation is written in this manner. Okay. The previous equation, P is equal to sigma Cc prime AC plus M times ASC. This is equivalent area of concrete. Okay. Equivalent area of concrete. And then in this, actually, steel is actually replacing. Steel is replacing a certain amount of concrete. How did you introduce this steel? Without replacing concrete, you will not be able to put in this steel. That area is also taken into account. Okay. So total gross area multiple minus area of steel that is replaced. Is it clear? Area of concrete is gross area minus gross area minus area of steel that is or the steel area of concrete that is replaced by the steel. So then this equation, this P equal to sigma Cc prime, we can express this in terms of gross area, Ag plus M minus 1 ASC. This equation, okay? Any questions here? Any questions here? So basically what we are doing, if you want to replace or if you want to convert given reinforced concrete section into a homogeneous plain concrete section, you multiply area of steel with the modular ratio and also take care of whatever concrete that is actually replaced by the steel. So if you don't have any questions, that means I'm assuming everything is clear to you. Okay. So can we proceed further? Okay. So now whatever we discussed, that we can actually put it in the form of a figure. Okay. So whatever equivalence, whatever we mentioned, like in the form of equation and other things, we can actually convey that message using figures. So this concrete, this reinforced concrete column is there with rebars in compression, four rebars at 4 corners. And this is how this concrete section, reinforced concrete section, can be shown as an equivalent plain concrete section. Okay, you can see here this original this gross area is shown here inside, and whatever this area of steel is there, whatever this area of steel, that is disposed in the form of equivalent area of concrete. Equivalent area of concrete. And what is the amount of equivalent area of concrete? M minus 1 ASC. I explained to you why this M minus 1 is coming. Because we are some portion of area is replaced, of concrete is replaced by the steel. That's why this minus 1 is coming. Okay. Is this clear? And if you want, you can actually represent this same thing idea in the form of this figure C or in the form of figure D. And just a suggestion, whatever in whatever way you want to represent or dispose this steel area as an equivalent concrete area, you can do it, but make sure that the center of gravity of this equivalent area matches with the original center of gravity. You can see here center of gravity of these four rebars is going to be at the center. Same way, even the equivalent area CG is going to match with the original CG. Okay, same thing even in this case and even in this case. Any questions? And tell me.
If someone is asking a question, then you have to unmute yourself. We are not able to hear you.
Okay. And here it is shown as divided by 2. That means it is disposed on both sides. This is disposed on both sides. That's why it is divided by 2. Okay. Okay. And now, if that is clear, whatever reinforced concrete column section that I showed you, if that is clear, let's see a reinforced concrete beam section. Okay. Reinforced concrete beam section. Please note that reinforced concrete beam, let's say that section is actually shown here in this figure. This is a rectangular beam, rectangular cross section, a beam having rectangular cross section, and area of steel. Steel is provided in the bottom portion, and assuming this beam is undergoing sagging moment, bottom fibers are going to be in tension. So to take care of that tension, because concrete is weak in tension, and we are providing some steel here. And those steel bars, whatever we provided, those please note that this is a section. So these bars are going to go out of the plane of this board or out of the plane of this screen. So they are called longitudinal reinforcement bars. So this longitudinal reinforcement bars, the total area is AST. Okay. So now you have a rectangle. Imagine you have a rectangular section beam, reinforced concrete beam having this area of steel in the bottom, and you are subjecting it to sagging moment, and you keep on increasing the load. Initially, you may be starting with smaller loads, and beam is going to have certain capacity before it cracks and other things. Anyway, so you start with initially with smaller loads. At that time, what is going to happen is entire section is going to be in entire section. The stress distribution is going to be something like this. Strain is going to be linearly varying. Plane sections remain plane before and after bending. That is based on that assumption. Strain is going to be linearly distributed, and assuming the strains are not very high values, we assume stress strain relation is linear. That means the Hooke's law is valid. So stress distribution is going to be something like this. Strain distribution is linear, stress strain relation is linear, so stress distribution is going to be like this. And what is this here? Stress in concrete. The top fiber is concrete. Stress in concrete in bending compression. Okay. And at the level of steel, and now you use that formula. Use that equation. F2 is equal to M times F1. F2y is equal to M times F1y. So at the level of steel, the concrete surrounding the steel, in the concrete surrounding the steel, and also please note that we are assuming perfect bond between steel and concrete. Only under that condition, strain distribution is going to be linear. Okay. So this value of stress that is shown here is stress in the concrete surrounding the steel at the level of the steel. So that value, what is the stress? F1 or F2 is equal to M times F1, and F1 is equal to F2 divided by M. So here stress in the steel divided by modular ratio, that is going to give you equivalent stress in concrete surrounding the steel. Okay. So that is this stress distribution. And just now I told you, we are loading this beam. Initially, this entire section is going to resist the load. Entire section is going to resist the load. In the sense, the top fiber is going to be in, we are subjecting it to sagging moment. Top fiber is going to be in compression. Bottom fiber is going to be in tension. Please note that concrete is having certain capacity to take care of the tensile stresses. The permissible or the tensile strength of concrete can, without using any of the formulas, tensile strength of the concrete can be taken as 10% of its compressive strength. So initially, when you apply smaller loads, even the bottom, the concrete which is below the neutral axis, whatever concrete is there, that also will resist some stress, tensile stress. So that's why entire concrete section is going to be effective. Okay, whatever fibers, whatever portion which is below the neutral axis, that's going to be in tension. Whatever portion that is above the neutral axis, that is going to be in compression when you subject this rectangular beam cross section to sagging moment. Okay, so now initially when the load is small, the entire section is going to be resisting. Even concrete is going to have certain capacity to resist the tensile stresses that are coming. So this is this shaded or hatched portion is the concrete area. And what about the steel area? Steel I am going to convert into equivalent concrete. Steel I am going to convert into equivalent concrete. And the steel, what is the equivalent area of concrete? Modular ratio times area of steel. And also we need to take care of whatever portion of concrete that is replaced by the steel. So that's why you have AST, M minus 1 AST, M minus 1 AST. And here in this figure that is shown as though it is disposed equal on either side equally. Okay, so half of M minus 1 AST. So this the first figure corresponds to the case of a reinforced concrete section beam with the area of steel in the bottom region subjected to sagging moment, and when the loads are not that high, the entire section is resisting the load that is applied. Even concrete can take some certain amount of tensile stresses. Okay, that is figure A. If you are at that stage, this is your equivalent section. Let's assume you keep on increasing the load, and when you keep on increasing the load, what happens? The concrete below the neutral axis, it's going to be subjected to tensile stresses, and the tensile strength of concrete is only 10% of its, approximately 10% of its compressive strength. So when your tensile stresses increases, concrete below the neutral axis is not going to be effective. It's going to get cracked. It's not going to be effective in taking any of the tensile stresses. And then only steel is going to be effective. Steel is going to be effective. So this is the case for that. Okay, this is the case when concrete below the neutral axis cracked. What is the equivalent section in that case? That is shown in figure B. Okay, and you sometimes you may we will see in detail when that situation is going to be there. Please note that steel is good in both in compression as well as in tension. Steel is good both in compression as well as in tension. So we can even provide steel. Please note that if you take a rectangular section subjected to sagging moment or hogging moment, the extreme fibers are going to be subjected to the maximum stresses. So if you say this is a rectangular beam and it is a rectangular section beam and it is subjected to hogging moment, top fibers are going to be in compression, bottom fibers are going to be in tension. Even the top fibers in compression, if you want to reduce some load on the concrete, you can provide, or some steel can be even provided in the top layer where compression stresses are more. Okay, so that is this kind of beam. The third figure is showing a beam in which you have steel in compression as well. Steel in compression as well. And now in that case, what is the equivalent section? Again, let's assume the load it's subject, this kind of beam is subjected to hogging moment, and I keep on increasing the load after the concrete below the neutral axis is cracked. So the effective section is going to be the section of the concrete which is above the neutral axis, and also tensile steel equivalent in terms of concrete, modular ratio times AST. Okay, modular ratio times AST. Or you can, and please note one more thing. Once the concrete cracks, you can just simply say m minus 1 is not required. M times AST. Here the equivalent area of concrete, this steel, if you want to replace with the equivalent area of concrete, since the concrete below the neutral axis is cracked, it is m times AST. Okay. So here in doubly reinforced section, this is a reinforcement is there on the top as well as bottom. That's why it is referred to as doubly reinforced. Okay, reinforcement both in compression as well as in tension. In that case, equivalent section after the concrete below the neutral axis cracks, it's going to be something like this. Whatever area of steel that is there in the bottom portion, that is converted into equivalent area of concrete by multiplying with modular ratio. And please note that concrete below the neutral axis is already cracked. It's ineffective. So that's why m minus 1 is not there. And in the top portion, you can see top portion, steel is there. That steel, what is our understanding so far? Whatever area of steel that you multiply with modular ratio. And if you want to take care of the concrete that is replaced by the steel, then you just write it as m minus 1 times area of steel. But what is written here? 1.5 m minus 1 AC. What code is saying is when the steel is in compression, you take modular ratio based on this suggestion is based on long-term effects. Long-term effect. The behavior of concrete in compression is going to be different from behavior of concrete in tension, and if you consider long-term effects as well, okay, inelastic strains. So then the code is suggesting instead of m, if the steel is in compression, you take it as 1.5 times m. You take it as 1.5 times m, and this minus 1 is to take care of the concrete that is replaced by the steel. So these are the equal transformed sections. This figure, the middle figure is showing the transformed section for different categories. Okay, rectangular section, singly reinforced or reinforcement only in the tension side when the load is not that high, the first figure, and when the load is high, concrete below the neutral axis is cracked. In that case, what is the equivalent section? And if you take a section which is reinforced both at the top and bottom, and once the concrete is cracked, what is the equivalent section? That is shown here. Okay, and the corresponding, the third figure is showing the stress distribution, equivalent or the stress distribution for transformed section. Okay, any questions here? Professor Amlan, you want to add something?
See, you have to appreciate that the concept of modular ratio is empirical, especially because we are treating concrete as a linear elastic material. See, that's why, see, all these factors like 1.5 times m, these type of factors are brought in to take care of the nonlinearity in concrete. Concrete is actually not a linear material, but we have simplified it to be a linear material. And hence, to take care of this long-term effects and all, this type of factors are brought in. Okay.
Okay, I'm going to stop here because this is a very important concept. I want to give you some time for digesting all these concepts. And any questions here?
Sir,
Yes.
sir, how do we determine the failure, sir? Means when the concrete is cracked or when the steel fails?
No. Just you are like jumping ahead. We will discuss it in tomorrow's class. Okay. For the sake of other students, what he is asking here, I showed you two cases. First case is assuming the loads are small, the entire section is effective. Second case is when suppose I keep on increasing the load, at certain point the concrete below the neutral axis may not be able to take any more, its capacity may be exceeded. In that case, it gets cracked. So the question is, when do you decide? So that we will see in tomorrow's class. Okay.
Okay. There is one more question regarding that 1.5 times m minus 1.
Sure.
Why is it like that? Let me just reiterate.
Let me explain.
Yeah.
Forget about this 1.5. Forget about this 1.5. M minus 1. That there is no issue with that. No, there is no issue with m minus 1. M is modular ratio. Minus 1 is just we are taking care of whatever concrete that is missed out because of placement of this steel. That's why it is. And what is the area of concrete that is missed out is equal to the area of steel that is actually there. So that's why that minus is coming. And for compression, code is saying instead of taking m, you take it as 1.5 times m, because at higher loads, at higher stresses, the inelastic behavior of concrete is going to be different in compression when compared to in tension. And also taking care of all the long-term effects, code is recommending instead of m, you take it as 1.5 times m. And this is what Professor Amlan is saying. This 1.5 factor is empirical one. Okay. Professor Amlan, you want to add something?
Yeah. Let me just explain this way. See, with time, concrete creeps, means it deforms. I can put this in another way, that concrete, the stiffness gets reduced. That means the EC of concrete, the modulus, gets slightly reduced with time. Now, if the modulus of concrete gets reduced, then the modular ratio, which is the ratio of the modulus of steel divided by the modulus of concrete, should increase. And hence, to take care of this increase in the modular ratio due to the effect of creep, the 1.5 factor has been placed. This is for a long-term loading when concrete gradually deforms more than what it deforms if you load instantaneously.
Any questions? Okay. Any further questions? And I also want you to pay attention to the third figure. Okay. Third figure is giving you the stress distribution. And in tomorrow's class, and this is what we will be actually making use of it. Okay. This stress.
Okay, but let me just quickly reply to Yuvraj's question. See, cracking of concrete is not considered as a failure because we are placing steel. There is redistribution of stresses. The stress which concrete used to carry before cracking is picked up by the steel. And hence, cracking of concrete is not considered a failure. Definition of failure, we will come to it later.
No questions? Then we'll stop here. But what I suggest is, I think you have to pay attention. You have to be more serious from now. Okay. It's not that you are not serious. I'm happy that all of you or most of you have submitted your assignments on time. But what is that? Some